All right, got the recording going. Um, so I'll pull up my slides again. So I just mentioned this talk will be slightly less technical than usual. So this is kind of a storytelling of just the history of large language models and natural language processing. So I had the kind of interesting experience of I got into ML before um, large language models and BERT and all of this stuff came out. So I think I kind of have an interesting story of like how these things have progressed, how everything has changed over time, what the major breakthroughs are. And so I'll teach the pieces a little bit, but it's mostly focused on just like here's the big breakthroughs and what hurdle that got us over every single time. Um, so goal of the talk, walking through just some of the history. So starting back in the 1960s, there was interest in this stuff, but it really just wasn't possible. We didn't have enough compute capacity. We didn't have the algorithms. We didn't have all of this stuff just wasn't developed yet. People had the ideas, but it wasn't fully baked. So I'm planning on going a little bit back that way, but most of the focus will be kind of like 2013 till present, because that's the part that I really, really know about. Um, so I'll touch on some of the super popular systems throughout the talk. So there were certain kind of landmark pieces where we really covered huge advancements. So we'll go from the very simple when things were just starting all the way to the complex of modern day systems. And then I'll also walk through some of the different problem types. So when we were at the very simple phase, people were only thinking about solving one individual piece of the problem or trying to do parts of speech tagging or some individual thing. And then we've kind of evolved to like, let's just build this intelligent system that can do whatever we ask it to. So if you walk away from this talk with a little bit understanding of the history and some of the hurdles that we've gotten over throughout the time, that's the whole goal. So I wanted to start with ELIZA just because I think it's an interesting case. So this was before we really had the capability, people had the idea of a chatbot. So it was like, what if a machine could talk to us back like a human? Um, so this is a link I can pull up, and this is an interesting system. So the idea back in the day was basically let's make a machine respond back like a human in some way. And the way that they formulated this was like, let's make it a therapist. And the easiest, most like constrained problem is it's just always asking you a question back to try and continue the conversation. It doesn't need to actually give you any like valuable information or do anything transformational. It can function as a therapist, just kind of like guessing the right thing to respond back to you. And the way that this was developed um, was a bunch of rules. So they basically, it's just a whole bunch of if else statements and a little bit of extra like parsing on top of it. So they're trying to extract certain things out. So like if you just say, hi, Eliza, um, thinks for a little bit, and then it was like, what would you like to do today? And then ask it, can you give me relationship advice? Um, and then it asks, don't you believe that I can give you relationship advice? And then you say yes. And it will do some chat back and forth. So it asks, are you sure about that? Yes. And then it gives you this canned response and it starts getting frustrated. Like, why do you just keep saying yes? Because it doesn't really have much memory. It's just kind of looking at one message at a time. Um, so just that's a little bit of history. Eliza, this early chat system before we were really there. It was like, okay, here, how do we make this work? And it was basically just a whole bunch of rules and someone hand coding. How do I make this stuff happen? And so I want to cut to current day. So most of you probably familiar with ChatGPT. So all the way to present day, you go to ChatGPT and you ask it basically anything, and it can have a cohesive conversation with you about it. It's maybe not like expert in everything, but it's pretty good at whatever you want to give it. Um, so going back to ELIZA in the early NLP days, it was just rules. It was just someone has to actually code this whole conversation. So if you respond in some unexpected way, it really doesn't know how to react. Um, I'm gonna pause for 1 second. I don't have access to full view of chat and everything. I'm gonna pop that out. Um, all right. Um, okay, there we go. Um, so yeah, this ELIZA is very important historical system, but it really is not very capable. If you sit there and you try and interact with it, it won't do very much. Um, so that was kind of the rules generation. Everything is just hand coded. You just say, if I want this to respond in this way, then just code that up. Say, if this, then that. And eventually we got to the point of like the statistical revolution where it's like, okay, we can't code every possible outcome. We need to do something that just learns from open text. So there's this famous quote from one of the lead people at IBM, and they basically said, every time I fire a linguist, the performance of our speech recognizer goes up. So there was this point where they had like all of the smartest linguists and they're trying to code up all of the rules and they're saying, okay, when this phrase happens, it's this certain part of speech and dependency parsing and all of this other stuff. And um, it just really wasn't scalable. It wasn't able to generalize to new situations. And so eventually the statistical mindset came in. And so it went from handcrafted to statistical. And then we started getting stuff like hidden Markov models and n-grams and scaling up data. So at this phase, the big like advancement was these n-grams and hidden Markov models. So the whole idea here is basically saying like, given the last word or given the last two words, what's the most likely next word? And so with this, they could do things very simple. So like if you're given the word beautifully, then what's the next word? What's the probability of it being blue? And so this is very limited because the way that the English language and other languages expand, if you look at more and more contexts, it just becomes like physically impossible to cover everything. So even if you said like Ryan is studying natural language processing, it's possible to plug in a million different names in that first part, and you aren't going to have good coverage of all of those different scenarios. Um, so I wanted to point out there's this book. Uh, I'm not sure if I can say the last name properly, but Dan Jarafsky, very good books on these topics. This is one of the things that I started with. So the 2012, 2013 version of this book was going through a lot of these different concepts. And that's one of the places that I started learning from. And it started with the n-grams and the parsing and hidden Markov models and all of that stuff. So if you want a history lesson, that's a good book to start with. Um, so with the n-gram stuff, I can post the link to all of this stuff at the end, or actually I'll give the link to the slides and then you can have everything in there. Yeah. So here's the whole presentation. So the links will be in there, and everyone can click through stuff and play with them. So the n-gram stuff, the whole idea is looking at, like, I was given this word, what's the most likely next word? And so the idea here is you can make this massive grid, and it's saying, if I have this word, then what's the next word? And so what this table is showing is basically, if I have the word I, what's the most likely next word given the data that I've looked at before? So in this data set, want is a very common next word. Someone might say I twice for some reason. They might say I eat. They might say I spend, but they would never say I food, I lunch, I Chinese. And so you can see these words as you go through the whole set. So saying what's the most likely word after want? Probably to. You could say I want Chinese food. You could skip the to eat and all of that stuff. So this is the way that things worked with the n-grams, is basically saying I have these words, what's the most likely next word? And you can expand this to look at 2 words at a time instead of just one. So this is just looking at 1 gram, but you might have bigrams or trigrams. And so you might be looking at longer and longer history, but you run into that problem I was talking about, where it's like, if you look at the previous 5 words, the likelihood that it's just totally unique and you have no data representing it is very, very high. So this was, that was the common technique of representing text for a very, very long time. So just basically counting the words and saying what's the most likely given the previous combination. So just with this alone, they were able to build certain things like predictive text. So you could see how that starts building into, like, I'm typing something, I have this word, what's the most likely next word? You already start getting sort of autocomplete based on that. So you can do it at the character level, saying like, what's the most likely next character? Or you could do it at the word level, saying what's the most likely next word? And you already get these amazing properties out of that. And you can use it in like many different cases on keyboard stuff on phones and wherever else. It started the beginning of machine translation. So we could take small phrases and say, like, from French, turn this into English. And so the way that people did that initially was they had all of these aligned transcriptions from like UN proceedings. So the UN has a meeting, they have to translate things into 80 different languages or something to be in a format that everyone can read. And people said, oh, this is an amazing data set because I can align all of these phrases and then I can directly say, like, map this to that and then do translation in that way. One of the big pieces was parts of speech tagging. So just being able to say, okay, this is the verb in the sentence, this is a noun, this is adjectives. And so people went down very, very deep paths trying to say, how do we get parts of speech out? How do we get named entity recognition? That was a very common problem back in the day. Like, I'm reading this news article and I just want to pull out all of the companies' names and the people's names and the different places that are mentioned and stuff like that. And then people were also concerned with things like dependency parsing. So the whole idea of, like, Ryan is studying NLP with Dan Jarofsky's book. He thinks it is very good. And then dependency parsing would be saying, like, what is it referring to? Is it referring to Dan Jarofsky? Is it relating to the book? And so that became a very big interest of people. And then on top of that, people are also interested in information extraction. So you read an article and then you want to be able to say, like, pull out just 3 sentences that summarize the whole thing, or pull out the key events, basically. So one thing I wanted to show, so this is Spacey. This is still a modern library, but I wanted to show it because it shows a lot of the different pieces that people use throughout. So I'm mostly showing this just for the visualizations. So this is showing, like, they have this complicated pipeline where they can turn this sentence, Apple is looking at buying UK startup for 1 billion. And so you can see they're processing it in all of these different ways, trying to fill it up with a whole bunch of metadata basically. So here's the lemmas, here's the parts of speech, here's the tagging, here's the dependencies, um, all of these different pieces. I don't know what all of them are, but you can see they build up a graph like this, saying like, here's the relationship between all of these words. This is referring to that. It's a verb. It's a proper noun. It's an adjective, and so when I started, this was a very common thing that a lot of people were concerned with, was you would build this crazy pipeline where you're trying to get it to do many different things. And it might be composed of 8 different models, all trying to label the text in a bunch of different ways. And then you might use that in order to build something useful on top of it. Let me So this is what it might look like. So they're showing this processing pipeline and they're saying you have text in and then you do all of this stuff on top of it. And then you have this sort of like annotated document. So Spacey, still a good library. They've started integrating all of the embeddings, large language models, all of that stuff. But I just wanted to show it because I think they're one of the best at visualizing like all of the different stages of this stuff. Another classic one I wanted to touch on. So this one is so old now that no one really uses it, but it used to be common to use this library called NLTK, called Natural Language Toolkit. And so the whole idea was this is a whole bunch of useful like text utilities. So this one is just showing like we have this sentence, we want to break it into words. And you would think that's pretty simple. You just split on spaces or something like that. But it's actually a little bit more complicated than that because you might have random punctuation, you might have periods in weird places, you might have all kinds of different stuff. So people have figured out good ways to actually make sure that you're splitting into words and not other things. And NLTK also had the similar stuff like Spacey did in terms of parsing it into a tree and stuff like that. So at one point, NLTK was like the dominant like natural language way that you handle things, but at this point, it's definitely gotten old and fallen off. So one of the things that I want to highlight with this is the whole focus was just everything is custom. Everything requires its own model. You can build up some pre-existing pieces, but then in the end, if you want to do something, you have to actually customize it to do your certain thing. So narrow AI here, very, very focused on individual pieces. It's not general purpose yet. So one of the big advancements was bag of words. So this one is a little bit strange. So the previous method, hidden Markovs, n-grams, you're looking at the next word. So you're kind of focused about the sequence of things. But bag of words, what you're saying is basically don't care about the order of words. It's like, imagine your like Scrabble tiles in a bag. You're saying just like every word has its own tile, throw it in the bag, and then how much of each word are there. So bag of words, you had stuff that was basically just saying how common is the word apple? How common is the word soccer, for example? So you're just counting up the words and saying, okay, this document has a lot of mentions of the word soccer, so it's probably an article about sports. And so this bag of words approach was very, very useful because people started going into focus stuff on retrieval and search. So imagine like Google, you want to find the web pages that are relevant to a given query. And so they would do something like say, okay, count up all the words. And then if someone searches up soccer, then they want documents that also mention that. And so whichever ones mention that a whole lot is probably a useful way to search based on that. But one of the advancements on top of that is if you're just looking at the raw counts of these words, the problem that you run into is there's certain words that will just completely dominate. So like the, of, it, and there's certain words that they just happen a ton of times and you really don't care about those words. Those words don't hold much signal for you. Every document's going to have those, so you don't really care. And so the innovation that people applied on top of this, they called inverse document frequency. So term frequency, inverse document frequency. And the whole idea here is basically you want to scale the different counts based on how many different documents had that same word. So if you have the word marble and it only happens very, very rarely, it doesn't happen in that many documents, but one document has it, that's one you really want to focus on when someone is searching up the word marble. And so this IDF is a way of scaling based on like your previous documents, and you go, okay, I know that this is a high signal word because it doesn't happen very often, and it happened in this specific document. So the TF IDF became kind of the dominant representation of how do I sum up what's inside of a document. So these are extremely powerful. They persisted as like the dominant representation, I would say, up until 2010, 2013. But the big downfall of it is it has no knowledge of the ordering of words. So it's just counting. And so if you say like someone hit someone else, it doesn't matter the direction of that, how that happened. It's just saying, okay, this name hit that name, both of them get a count of one. So you have no way of understanding the direction of relationships and stuff like that. So very powerful representation, but has that key flaw of like, it doesn't really understand language. It can kind of get the gist of some text, but it doesn't really cover like what we think of as language. So it's useful for stuff like clustering and topic modeling. So someone might say, okay, DF on all of my documents, and then form clusters out of it, and then look at those clusters and say, okay, here's all the documents about sports, here's all the documents about politics, here's all the documents about business. And so you could do clustering and topic modeling based on something like TF-IDF, but you couldn't really do that much beyond that. You could do certain classification things, but you couldn't like generate text or do a chatbot like Eliza with it. So the next step beyond that, so going to word embeddings and neural networks. So the key piece that we were missing before was the bag of words. It's just counts. It doesn't tell you anything about the words. It doesn't tell you anything about similarities of words. And so what people wanted to do was they wanted to figure out, how do I actually like pack some meaning into the word cat or dog or father or something like that? And what people did with Word2Vec was they figured out, if we do this task with a neural network trying to guess, fill in the middle. So this sequence they have here, the man loves his son, they would give the neural network the man, his son, and then they would say, what was in between there? And so over time, it's learning what context do these words appear? What is the most likely outcome in this specific place? And so during this learning process, it's figuring out, okay, which words go where and what is their meaning? And so what happens here is you build this model, and then it has to create some vector that kind of captures similarity and meaning with other words. So you could even have like, so this one says the man loves his son, but you can think of like what other words might possibly fit there. So the man hates his son, or the man feeds his son, or something like that. There's many different words that could fit there, but if you do this over and over again with billions of words, eventually you get something that's pretty knowledgeable and kind of aligns with roughly what it thinks the words means. So this word embedding approach was really the next level of like, now we have something that understands the word actually, instead of just being, okay, the word soccer happened 10 times, for example. So I'll pull up, this is a site that is showing the visualization of these word embeddings. So if we dig into some random grouping, this is trying to map similar words to similar space. So this is initially the word embeddings are 300 dimensions, and then they do a trick to reduce it down to 3D so that we can actually visualize it. And then if we kind of dig around in this space, we can see the words that are close to each other generally have similar meaning. So this is a cool tool if anyone wants to go play around with that. There's a bunch of cool stuff that you can see inside of there. Um, So one of the things that they found was you map these things into high dimensional space, and it's trying to capture, okay, what does man mean? What does woman mean? And then they figured out we can do this interesting trick where we say man minus woman plus king, and you end up very close to queen. And so you have these interesting relationships of embeddings where you can kind of walk through this space and understand, okay, what does this mean in reference to this other one? So one of the weaknesses with this, though, was you only have one representation per word. So if you have something like riverbank, financial bank, bank shot, all of those the word bank maps to uh, a single embedding. So you have a single 300 dimension vector that says, okay, all of these in one piece. And so these embeddings are very powerful, but they have that fatal flaw of, like, if you go to the dictionary has 8 different definitions for one word, and this is saying basically you have to find some like average between all of them. So it's not very contextual. So with these embeddings, it's stronger than TF-IDF in many settings. And so you can do something similar to the bag of words thing, but instead of doing bag of words, you do bag of embedding. So you say, okay, embed all of my words and then average them together. And then you get some new vector that's supposed to represent what your sentence or document or whatever represented. Or one of the other common approaches was people started using RNNs and LSTMs and other like sequential processing models. And you could say, okay, take this sequence of embeddings and then process them with some sequential model and get some result out of that. And so in that way, we finally solved, like, okay, we have some meaning of these words and we also have the ordering of the words, so you can understand some deeper relationships there. So one of the problems with these methods, though, was that you needed a different embedding for every single spelling of words. So if you actually dig through these embeddings, they went through like web scale text, all of these words, and it's got all of these different typos and people just talking in online speak. So you would have a different embedding for hello with 2 L's, 1 L, 3 L's, however many L's, and all of those have their own separate unique embedding. And you're hoping that the model kind of maps them to similar space, but it's really not very smart to have this vocabulary of 3 million words potentially, and it still doesn't have full coverage of things. People are going to misspell and come up with new things, and so your vocabulary is very incomplete. So Word2Vec had that problem of, like, it has this huge vocabulary and it still doesn't cover everything. And so people started worrying about out of vocabulary tokens. And so the way that they solved that in fast text, which was a paper from Meta, they figured out we can split these things into little sub pieces of words. And then if you're missing a word, you can reconstruct it based on the pieces of things. And so that was very powerful, because if you had something like biology, you can split it into 2 different pieces, bio and ology. And then eventually you build up a strong representation of ology. And then anytime you see a new kind of science and ology, you can piece those together and you still have a representation of that word. So when I was first starting, I did some competitions, and this was a big piece that people were able to innovate on, was basically look at our data set and we have all of these words that are just getting no mapping. They're mapping to nothing. We don't have embeddings for these. So how do we solve that? And so that was one of the innovations that people were able to come up with, is like, it's better to map it to something than have it just be zero embedding or something like that. Um, so when I was first starting, there was this GenSim library, and one of its main values was you could actually train your own Word2Vec and all these different things on top of it. So this was a very valuable tool to be able to say, okay, I can download the Word2Vec embedding straight from Google, but that's limited to whatever data they ran on. I have a new medical data or financial data or some specific tech data, and they just don't have the vocabulary that I need. And so you could go and run Word2Vec on your own text and then say, okay, now I have embeddings for my own vocabulary, and I know that I have better coverage of this stuff. So GenSim not used very much anymore, but interesting historical point along the way. So that was the Word2Vec approach, and there's Glove and FastText and all these other ones, but all of them had kind of the same flaw, which was they had a single representation of every single word. So you have this embedding and it's just frozen. You have no way of updating it or making sure that it's pointing to the correct thing. And so the next level on top of this, people figured out, how do we make this so that it actually understands the context of the words? So instead of having a fixed embedding, I have some starting embedding, and then I look at all of the words next to it and I say, what's the interaction with the surrounding words? So in the case of like riverbank and bank shot and financial bank, it looks at the words that are next to it and then it contextualizes it. So instead of just being like, this is my single vector for bank, it's saying, okay, look at the words next to it and kind of build those relationships up and understand in the later layers of my network, now I have an embedding that is actually like properly contextualized. So it knows what the pieces are. So this is what things would look like inside of BERT. So you can see its input is like all of these different tokens. And so this over here is an example of what the subword pieces is doing. So like I was mentioning with biology, you split it into two pieces and you have bio and ology. With this, we have play and ing. And so the way that they would represent this is they would say, okay, we have play and ing. And to represent that the ing is just a continuation, we have this double pound. So the BERT and GPT and all these other models started being built off of this idea of, we need to like get deeper embeddings that understands the context that they're placed in. And so they train them similar to Word2Vec, but with slightly different objectives. So with BERT, the main objective was to predict the masked word. So imagine you have a document, it has 100 words, and then 15% of them, you're going to just blank them out. You're going to make them invisible to the model. And then you're asking the model, okay, fill that blank back in. And so it's very similar to Word2Vec, but it's just larger scale. It's saying for the whole document or for the whole paragraph, try to fill in multiple words at once. And then the way that this works is it's building up these deeper representations because it's going through multiple transformer layers, and then you keep that entire encoder basically. So you pass these embeddings through, and then it's saying find all the interactions between all of these, figure out the context of them, and then at the end you have these embeddings that have like encoded the context into the embeddings. So you have a much better representation of what things are representing. So the key point here is BERT is predicting the masked words, and then the next level, people started playing with GPT. And so the idea here was, instead of predicting the masked words, you predict all of the next tokens. So this is going more back to that like hidden Markov model style where you're saying, guess the next word, guess the next word. Okay, given these previous 8 words, guess what the next most likely outcome is. And so one interesting historical point for me was I played with both BERT and GPT was way worse at the time. So when I tried to do my classification and the kind of narrow tasks that I was interested in, GPT was way worse and way more parameters. So if you look at the size of the models and you say, okay, this GPT was 1 point something billion and this BERT model was 110 million or something like that, and I was getting better results out of BERT for my narrow tasks. At that point, I was kind of like, why are we doing this GPT thing? It doesn't make any sense. But we'll talk about it more later. But it ended up opening a lot of doors. So one of the things that made GPT possible, though, was this transformer architecture made it so that we could simultaneously predict all future predictions given a certain context in a single pass. So in the past, people had tried to do similar stuff to this, but you have to just loop over and over and over again, trying to get next word, next word, next word, next word. And so it was very inefficient to try and go over your entire data set and say, predict the next word and just keep going. So the transformer architecture made it so you pass it like the full set of text and you just say at every position, guess the next position forward. And you could do that in a single pass of the model. And so it made it way more efficient to train these models. So that was one of the big innovations, was being able to parallelize that and make it so it predicts the entire thing in one pass. Made it much better to train than previous. So GPT, it was okay, but it was really not that great. If you tried to talk to it today, you would be very, very disappointed. It can sometimes make cohesive sentences, but sometimes it can't, and very often it just won't respond to you in a very intelligent way. But then people figured out, okay, if we make this bigger and bigger, we do more compute, we do more data, we do more layers, we do more parameters, it gets smarter and smarter over time. So people figured out, they did these studies of the scaling, and they figured out, okay, we're not at max capacity yet. We just need to keep doing more of this and we can get better and better results. So we had GPT, and then they made GPT-2 and GPT-3, and they scaled that all the way up to 175 billion parameters, which was just completely unheard of for the day. It just didn't even make any sense to do that. But they were really reaching into the dark and saying, okay, how far do these scaling laws go? Do they just keep going into the future, and can we predict what the performance is going to be if we go even larger than that? Do we get some crazy emergent property? So GPT-3, they make this massive 175 billion parameter model, and they say, okay, it's really smart and it's really good at a lot of the stuff that we're interested in. But the like big unlock here was they figured out that it was what they called a few shot learner. And so in the past, whenever you trained a model, you trained it to do one individual thing, and you hoped that it just solved that one task. But with this new few shot learning setup, they figured out this model is already able to translate something from French to English, and we never trained it to do that. All you have to do is you show it a few examples of translating from French to English, and then give it another French word, and it will return back the English text. And that was very, very surprising, because it was like people have been trying to do translation all this time, and they've been training specific models for this. But all of a sudden, we have this model that is just doing it on its own. We didn't explicitly teach it to do this. And so GPT-3, the big unlock was realizing that behavior was like, this model is actually so smart that we tell it like, do this thing, and it can do this thing. It's no longer, I have to fine tune this model in order to do translation. It's packed so much knowledge of language, it can start doing it out of the box. So this is a very important paper. So that was like one of the biggest unlocks. But I would argue that the next step, the instruct GPT, is an even bigger step. So GPT-3 showed, okay, this model is very smart. We scaled it up and we know like, okay, these loss curves are going down, but how good is it practically? And that revealed a lot. But the big unlock was instruct GPT. And so this was the whole idea of basically right now, the model is just trained to predict the most likely next word. So it's just saying, I've seen all of Wikipedia, I've seen a bunch of the internet, and this is the most likely next word given the string of text that you just gave me. Instruct GPT was saying, well, sometimes you don't want the most likely next text. You're trying to guide it in some way. So imagine you have like a math worksheet or something like that, and you say like you give GPT-3 an example of a math problem. Instead of trying to solve that problem, it might say, oh, this is problem number 7. I'm going to generate problems 8, 9, 10, 11, 12, because when I saw this on the internet, that was the likely next outcome. It wasn't the full solution. It was like, oh, this is a math worksheet. So now I'm in generate math worksheet mode. And so that's not really what many people wanted. And so what Instruct GPT was doing was saying, gather some human feedback data. So saying, I prefer this result over that result. When I ask this question, I expect you to react in this way. And it steered the model in order to respond with what the human wanted rather than what's the most likely next word. And so that was a very, very big unlock, because all of a sudden the model is following your instructions rather than just saying, what's the most likely next word. And so I would argue that this is like the most important step change, because before you could talk to GPT-3, but very often it would just not do what you wanted. And all of a sudden going to Instruct GPT and GPT 3.5, you were getting results back where it was like, this model is trying to answer my questions and do the task that I'm telling it to, rather than just being this kind of like unsteerable, intelligent, like text generator. So GPT 3.5 came out, and it had this amazing property that it can follow your directions and it can answer questions and do all kinds of stuff with your text. And immediately everyone goes, this is amazing. We need to figure out how to reproduce this, because we have this problem where all of a sudden OpenAI has this advanced model and no one else has it. So it put a lot of companies in a weird position. So when I was working at H2O, we had all of these models that were trained specifically for certain things, and it was just kind of embarrassing being like, okay, this model out of the box is doing better than something we worked on for 3 months, and they weren't even trying to do this certain thing. And so everyone said, we have to recreate this. We have to find some way to do something similar. And so one of the problems with this was that the resources in order to create a model like this, like not everyone is able to make a 175 billion parameter model. So we were just kind of at the mercy of, we hope some company releases a model that's equivalent or that we can play with, or some path forward in order to get parity again. And so one of the surprising heroes here was actually Meta. So I know a lot of people have negative opinions of Meta and Facebook, but they were kind of the unexpected hero because they started releasing this Llama series of models. And so that closed the gap slightly between what was available with ChatGPT and with Llama and other open source models. So if you look at this graph here, this is from Epoch AI, and they do a bunch of research on this stuff. And what they're showing is basically, here's the closed source graph. All of these models that you just have to go interact with someone's API and pay for it. And there was a point where it was like GPT-4 is just so far above everything else. How are we going to ever compete with this? And then Meta started hopefully chipping away at a bunch of things here. So Llama 1 releases, and it's a huge step change from like everyone is down here at 45% accuracy, and GPT-4 is up at 90, and Llama kind of helps close that gap multiple times. So all the way up to Llama 3, closing the gap, figuring out the pre-training steps, so train it on a whole bunch of internet data, and then also figure out how to gather data from that human feedback stuff, how to do the training process. So they really, really closed the gap with OpenAI. And so we've had multiple moments similar since. So one of the things that people have been measuring is what's the distance between open source and closed source offerings. So GPT-5 gets this amount of performance. How many months does it take for open source to equal that? And that number has actually been going down over time. So GPT-5 has whatever halo performance, and then we expect open source models to be able to match that within 6 months or 3 months or something like that. So that's one of the important metrics that people have been looking at over time. So we have these powerful text models now, but the other thing that people are very interested in is multimodality. So we have these smart text models, but one of their problems is people also want it to be able to see, they want it to be able to talk, they want it to be able to like interact with the world in a bit more diverse ways. So OpenAI released their GPT-4o, and this was a big step change because it allowed the model to speak and to see images and all of this other stuff. So they have some very interesting demos where they say basically, we've loaded this onto the phone and we can talk with you, we can look at the object that's on your desk, we can do interesting stuff with this. And so multimodality was a big step. And this followed a similar trend with the other systems. With the OpenAI released something, and then everyone said, okay, how does this work? How do we do this? And so we had stuff like Lava, and Quen has Omni models and other stuff like that. So slowly the gap has closed there as well. So another piece of this, so we saw the scaling laws of make the model bigger, train it for longer, give it more data. And that was very, very powerful for a while. And then it seemed like we hit some sort of a wall. So basically they said, we pre-trained this model is very, very smart, but it's still kind of inconsistent at certain things. There's certain things where it's like, it's just not very good at math. It gets functionally 0% at many of these things. And so the big trick that people figured out, OpenAI released o1, and that was what they called their reasoning model. And what this was doing was it was spending more tokens, thinking, and then finally spitting out an answer rather than just trying to do it in a single step. So imagine you ask it, what's 37 times 42? It could just immediately try to say, the next token is my answer. But a more powerful thing for it to do is to actually try and do step by step. Okay, 37 times 42, I have to do this operation, then that operation, then that operation. And so it's thinking with its tokens. It's saying, okay, break this down step by step and try and solve this problem. So this took a while to achieve because the difficulty is you could label a ton of data and say basically, okay, do a bunch of math problems and work through step by step and then train the model explicitly. This is the path to the solution. You need to output this token and then that token and then that token. But it's very difficult to do because you need to have at some points like expert people working through the problem and very detailed annotating exactly what operations they're doing. And so what they figured out you can do is some form of reinforcement learning where you can say, okay, give the answer, what steps do you need to take in order to get there? Whereas before, everything was densely supervised. It needed to know exactly the next token to guess at every single point. And this was much more unstructured. It's basically saying, try to get this answer and then just drop whatever reasoning it takes in order to get there. Um, so this was a very, very powerful paradigm shift because there's certain problems that it just wasn't able to do out of the box unless you integrated this trick. So similar trend as before, OpenAI releases O1 and everyone goes, oh, wow, this is amazing. This is hugely beneficial on certain benchmarks. And then this company, DeepSeek, goes and tries to reproduce it and figure out what's the trick that they're not telling us about. And then they eventually develop this R1 model. And this R1 model was a huge shock to many systems because it's this model that came out of kind of nowhere from China. And they were able to open source this and say, okay, everyone has this reasoning model now and is very, very powerful. Um, so this paradigm of test time scaling was a big shift in the behavior of these models. The being able to kind of scale up effort in the token space. So saying, guess more words, more words, more words, and then think about it, and then finally come to your solution rather than just saying, okay, right now, guess your solution immediately. Like it made it tractable to solve much harder problems and be much more consistent at certain things. So that brings us pretty much to modern day. So now the big move is agents. So the reasoning, the multimodality, the bigger and longer trained models on more data, longer context. So these models have been trained to work even if they have 100,000 tokens or something like that, even more in certain cases. They are now able to consistently enough do things that people are like, okay, give it a little bit longer leash. So before the behavior was very simple. I ask the model to do something, it responds back with some text, and then that's the extent of the conversation. And then I just have to continue it on in whatever way. And people figured out we can give the model certain abilities and then allow it to kind of drive itself. So if we put it in the right kind of control harness, then it will just continue doing whatever we're trying to do. So you give it the ability to call certain tools and interact with the outside world and get information back. Then instead of you prompting it over and over and trying to give it the right words, it will actually just go kind of discover and do actions on its own. So this has been very, very powerful for stuff like writing code, where you can basically say, modify my code base in order to do some certain thing. And then it will find which file do I need to change in order to make the code do what you want. And then it can actually run the code itself and double check that what it did achieve the certain goal. And then at that point, it can say, okay, I made all these changes. Is this what you want? And then you can continue the conversation from there. But giving it the ability to do multiple turns back and forth, just getting feedback from its environment is extremely powerful. So this solved a lot of problems, being able to say, okay, now the model actually has control of certain things. It gets feedback. One of the major things, there was a point where people were super concerned with knowledge cutoff. So it was basically this idea of like, this model was trained in 2023, so it doesn't know who the new president is and stuff like that. And so when you start making it more agentic and you say, okay, when it wants to find some information, it can go do a web search and other stuff like that, then the knowledge cutoff no longer becomes a key limiting factor. It can just go Google and say, okay, who was the president in 2025? And then it has no problem. It doesn't just have some memorized, crystallized fact from that point in time. Yeah, so that's my full history of LLMs up to present day. So one thing, just like yesterday or 2 days ago, this model Kimi K2 thinking came out, and people are very excited about that because it's one of the first times that people believe that open source LLMs have actually passed the closed source frontier models. People are very happy with that model. So just kind of like my little plug for modern day, things are still changing. We might have companies like OpenAI and whoever else end up in trouble because the open source has been going so fast. It's hard to extract money out of these models quickly enough in order to justify the cost of training them. So that's Kimi, Kimi, K2. Yeah. So that's everything I have for today. If anyone has any questions or wants to talk about anything, free to raise a hand and chime in.
I'm curious. I hadn't heard that the thinking Kimi model was outperforming frontier models. Is there any like particular benches or articles or anything that found interesting really as relates to Kimi?
Yeah, yeah. So the big one that I'll share these slides while I'm talking about this. So the big thing with Kimi that people are impressed by is that it was able to do many different rounds of tool calling. So the part that I just talked about with agents, one of the difficult things is like you ask it to do some task and then it has to go back and forth with like, go do a web search, go modify the code, go check what the weather is. Like it can do all kinds of random things. And Kimi was consistent across much more tool calls. So if you try this with Claude or GPT-5 or something else, it might be able to do 20 tool calls reliably, but after a certain point, it kind of like fills up its context and it gets a little bit less performant. And Kimi was able to go to 50 or beyond and still be able to kind of follow directions and get its task done. That was the part that people are mostly excited about.
Got it. Thanks. I'll look for that one.
Yeah, Bobby, is that a raised hand? All right. Any other questions? Any other topics?
Well, I think the big thing going on between all these models and that Sonnet's really good at is it wants to solve the problem, like complex problems, and it'll generate like 1,000 lines of code. So ChatGPT 5 is a downgrade for me from O3. And I think especially the open source models, I haven't gotten it to do anything like 10,000 words, that's for sure. But that'll be the interesting thing going forward is which models will solve high volume complex workflows consistently, so you don't have to worry about the workflow or the model.
Yeah, yeah. I've been using Sonnet 4.5 and GPT-5 kind of interchangeably, and my preference right now is GPT-5 because it's actually more terse. It doesn't output as many lines of code. What I was seeing with Sonnet 4.5 was very often it would be very verbose and it would like really document what it was doing and it would be very defensive of many different scenarios that might not even be likely to happen in the code. Um, and so I've been preferring GPT-5 in the past month or so because I think it actually just keeps my code base more compact.
Backward compatibility wrapper factory. Anybody?
Well, I think there should be a new study. It's like instead of all these benchmarks, it's like full awesome studies that take many prompts, and then you're solving a complex world problem that nobody's ever done before. And I'm seeing a lot of these. It's just like you're trying to get a home run with a single prompt, as opposed to like you need a whole workflow, because the whole reason of using this AI is to do something that's never been done before at scale.
Yeah. So on that front, there's this interesting study from Meter, and they've been measuring basically how long of a task are these models able to complete. They're saying that their study was basically, go have a human try to complete this. How long did it take them to do that? And then how, like, which models can complete that with 50% completion rate? So in theory, like if it takes 16 hours to complete a certain task for a human, then a model is very unlikely to be able to work for that long of a context and actually complete this stuff. And so this Meter study is basically saying how long of a task can it reliably complete. And in that regard, GPT-5 is one of the strongest, but it does depend on, are you expecting to give it one prompt and then it goes and it works for hours, or do you expect it to be a more interactive experience, saying like, okay, make a little change, is that correct? And then just kind of go back and forth with the model.
Hey Ryan, I have a question.
Yeah.
Have you had a chance to use K2 thinking on your agentic IDE to code?
I haven't tried it yet. I know that people are very excited about it on Twitter, but I've also heard mixed things. One of the problems that people have run into is like all of the open source models, they're trying to look impressive. So they're playing to the benchmark specifically. They're saying, how do I make this number go up? Whereas it seems like the frontier models are, they have their own internal benchmarks, and it's even wider than what's publicly available. So what some people have been saying is like Kimi K2 is crushing it at these benchmarks, but it might not be actually as useful in like broad other tasks. So I haven't tried it yet, but that's what I've heard from people. It only came out like 2 days ago or something.
I will mention that they released a CLI agent alongside it, if I'm not mistaken. So if one wants to experiment with getting it to code, that's probably the move.
Yeah, they did.
One other thing that I'll mention that just came out a few days ago. So this is kind of to Kevin's point of like discovering new things and solving new problems. This group made this Cosmos model, they're calling it. And the idea is trying to do RL to make it be a scientist and discover its own things on its own and be able to work for very, very long periods of time on its own. And they're claiming basically this model is able to discover new things, find data, run code, do all this stuff, and piece it all together in order to actually come to new conclusions in all these different domains. So biology and metabolics and all these different things, they're basically saying, look, we ran this model for a long time and it's discovering new things, or it's like confirming things that were known but never published. So they actually said, give this to a bunch of scientists, have them use it, run it in different ways, and then the model came to certain conclusions. Can we actually go run those experiments for real and see if we can reproduce what it thinks? So this is an interesting push in that direction.
Yeah, I know OpenAI 2026, 2027 saying part-time researcher next year, then a full-time researcher the year after that. I don't know if that'll mean like, searching the web, running experiments, publishing, putting it online, everything. I would imagine maybe not next year, but, fully autonomous, publications I see soon. I can generate as much as I want in my studies, but typically I need to really know what I'm doing in order for my prompts to get good. And I know what the LLMs are doing to get the output that I want. So it takes a fair amount of manual work, at this stage.
Yeah, yeah.
But I think the stepping thing is, that's what concerns me, is these things is like, well, what if you don't get what you want at the end of a couple hours? Are you rerunning this, or are you pausing it in between, or what's the workflow?
Yeah. They someone on Twitter was saying that they're actually charging $200 a pop. So you ask it one thing and then it will work for many hours and it costs you $200 for that single shot.
Really? I had no idea.
Um,
Wild.
so it depends on the context, because if you actually have faith that this is going to do something interesting for you, maybe it's worth a shot, maybe it's worth many shots. But that's a pretty steep barrier for someone to just try it. So very, very new system. We'll see where it goes. But
That's
yeah,
I think that's really interesting in terms of because for all these reasoning models, you're going to want to do data collection on user data so you can build data sets and improve the model later. And I think that should present a very interesting selection bias in that data set, right? Because you're going to get very different kinds of tasks and user interactions with a one-shot $200 a prompt thing than you are like $20 a month chat with this whenever kind of thing. I think that's very interesting.
yeah. You're selecting for people that are doing very specific things.
Yeah, for people that are going to write extremely detailed prompts to accomplish a goal for which they are willing to pay $200 for a chance at accomplishing that goal. I think it's a very that'll result in a very interesting set of telemetry that's very different from anything else, I think.
Yeah.
Yeah, another thing too is, with Sonnet, for me, it generated a whole machine learning notebook with 6 different models, plus the data set. Data set's 1,000 rows, and then the code is like 500 lines, 500 to 700 lines, and it ran like the first time. So, it's doing ensemble learning, it's doing all these different types of ML, and it just, like, pretty much every study it's like that, because this software is awesome. But I was like, it just did all of this machine learning. It found random forest was the best model. And then I asked ChatGPT 5, thinking for validation questions to ask to that model. And then so I went through all that, and it's just amazing. It's returning everything you need, not just a single model's worth. It's the whole notebook, everything included.
Yeah. They're very impressive.
But I think that'll be the thing in the future, is LLMs themselves be used for non-decision making purposes in regulatory environments like FDA required. And then you'll just generate all the code, and then the code will replace the human created code, as opposed to, you can't really verify an LLM. We don't really know how exactly it works. So if you're creating something, you can't go backwards and find out what its exact thoughts are, like you can with a known machine learning algorithm.
Yeah, very interesting times. We'll see what happens.
I mean, who knows? They could claim it's a breakthrough device. And if it's a worst case scenario, like, you need to keep prompting an LLM that you don't know everything is going on within, for the best of the patient's health, so they don't die. That might be a use case too. But I think for the more kind of routine stuff that you would want to have fully verified and validation, at every step, based on the code that you're running from the LLM, but not the LLM itself.
Yeah. One of the things that I was working on at my last company was, there's the agentic stuff, which is like, I ask it a question and then it does sort of like, it uses its creative problem solving in order to solve the problem one time, and it figures out, how do I compose all of my different tools and everything to accomplish a goal. But then one of the interesting things is, okay, it completed it once now. How do I just make it follow that given path every time now? Or how do I shorten that path? So if it needed to go do a certain web search and open a file and create a file, go write some code, do whatever. If you want that process repeated and done with new data or something else, you want it to follow a similar path. So one of the things that we were working on was we were calling it workflows versus agents, where it's like we want this process just repeatable and consistent and verified, versus like we want the model to be creative and try to solve this problem. I think that's an interesting avenue, because with the agentic stuff, you always have to ask it the next question, and you're bottlenecked by the human again. Basically, how much can the human ask the model to do? But when you start doing the workflow stuff and say just repeat this process but with different data or with different context or with whatever, then it becomes like extremely scalable again, where it's like we can do this 1000x, and it's not waiting on the human on the other end to push it to the next step every time.
I know people use LangGraph for that too.
Yeah.
Oh, so your company is building your own agentic system?
At my last company, we were, yeah.
Oh, okay.
Yeah.
But did you find with all the complexity, like you said, you could kind of get reproducible, but that seems to be the biggest issue is you get into all this complexity and you can't do your steps quick enough to solve the big problem, that it might just be better off using a single LLM alone. This is what I do, by the way, as opposed to getting into all this other stuff that could go wrong. It might run once and you're just constantly fixing that workflow kind of thing.
Yeah. One of the difficulties is the compaction of the path. So if you have the model be creative and try to solve a certain thing, it might go the wrong way 6 different times and then finally figure out, oh, this is what I want to do. And the artifact you want at the end is the cleaned up path. You don't want it to have to explore every single time. So that was the part that we were mostly interested in, is like it's actually wasting a ton of effort just trying to like resolve the problem fresh every time. Whereas if you just told it, do this, do that, do this, and then this is the outcome we want, then it can stay on the rails and be much more efficient than needing to explore every time.
Yeah, and I was saying to everybody too, you count the amount of time you spend fixing your AI workflow versus the amount of time thinking and solving the world problem. And if the first is greater than the latter, then you need to start reducing complexity and find something that runs consistently, and you can use it versatile, like across many different situations.
Yeah.
I have a question. So hypothetically, if you're like developing an LLM, couldn't you do something where like for any given response, it gives you the response, and then it also gives you like a seed or some kind of code to assign to that response? And then like if you really want to recreate something very similar to that response, but maybe only changing like 1 or 2 things, you could like copy the seed and then run your your altered version of the prompt with that seed, so it knows like, oh, I'm gonna like the user clearly liked this response because he's giving me the seed that was assigned with a different response, so I'm going to try to do something very similar to that. Couldn't something like that like exist or like be programmed into an LLM?
Kind of. It's a little bit difficult with LLMs because they're random. Like they're sampling from text, and they're going to get a slightly different result every time. And partially that's randomness of like the GPU is just doing math in different orders. But the other part of that is if you plug in different data, then it's all of a sudden got a different context, and it might decide to do things in a slightly different way. So the way that we were looking at it at my last company was, okay, solve the problem once, and then have the LLM look at its own history and say, what were the key successful steps? And then it can give it this sort of cookbook of like, okay, this is direction 1, direction 2, direction 3, direction 4, and then you hope that it actually sticks to that sequence of operations. So that was the way that we approached it, was basically like, okay, you got one successful run, now try to summarize it and make that the like proper path now. But you still end up with, in a lot of scenarios where it's just difficult to make it do exactly what you want. And sometimes it's failure of the summary, sometimes it's failure of the model adapting to new data. It works, it definitely works, but it's one of those things where it's like, if it works 50% of the time, 75% of the time, 85% of the time, sometimes that's just not good enough. Like if you're doing it out of business, it needs to work every time.
Yeah, I haven't. This is sort of a problem that we're working on over at my startup too, with there's that recent Thinking Machines article where it's like, okay, LLMs aren't actually non-deterministic. It's just that the GPUs that they're running on the way that they're being deployed introduces sufficient noise where you're going to get excess non-determinism that's really hard to manage unless you deploy it in this very specific way where everything is uniform. And I don't know if they have an associated release, but the basic issue is you have a large corpus of data, and then there are certain qualities of that data that you want to extract. And if you successfully extract those qualities, then what you get is a context bundle that you can pre-fill your next task with that successfully accomplishes the task. The problem is that when you're extracting those features from the large corpus, it's very easy to like not get the right context bundle out of that. So sort of the approach that we're taking is to essentially like store everything that could theoretically be useful to build that context bundle, and then RLHF on the context builder based on what people are saying. Yes, now that you have synthesized this collection of insights out of the large corpus of everything the model did, this is the one that worked, and then use that to inform further bundle extraction effectively. It's sort of basically our approach, more or less.
Yeah, interesting.
Yeah, and there's aspects I've found that are more reproducible than others. So generating tables with quantitative data, Sonnet does particularly well. But again, the way that it goes about solving the problem and all those other steps, I think at this stage, it varies.
All right. Awesome. We are almost out of time. I'm totally happy to hang out and talk if people want to keep talking, but if people want to drop, feel free to drop.
Thank you, Ryan.
Yeah, of course.
Thanks. This was awesome.
Thank you.
In terms of the closing, David mentions that ChatGPT has a seed and temperature parameter, and I know that is present in diffusion models, but does anybody have experience with language models that do have a seed parameter? Because I think they used to have one in an application I used to use called Better GPT, but it didn't really work. And I feel like there's some sort of, I think the point you make, Brian, about them being like sort of somewhat inherently non-deterministic, making it difficult. So like, yeah, I would be interested if anybody's seen like an implementation of seed in a language generation application that actually worked.
I don't think so. I tried several times with a simulation, and it obviously can generate the code, and then you change the seed on your own, and then you run the notebooks on your own. But Yeah, I think there's just too many moving parts, and there's not a full understanding of everything that it's doing in order for that to be the case.
So my understanding is it's possible with diffusion because what you're doing is you're giving it a specific pattern of noise to start with, and then the assumption is that everything after that is deterministic. So it will just get the same result every time. Language models, my understanding is that the seed doesn't control it in the same way. So you can have some seed that is trying to control some aspect of randomness, but even if you set temperature 0 and sampling off and whatever other tricks, and you set the seed, because of the way the batching and everything is done, like that's my understanding of the thinking machine's result, is like you get some amount of randomness. It's relatively small. Like if you run the same short query multiple times, you'll probably get a roughly similar result. But if you have like a very long text, you're pretty much guaranteed to get still a little bit of variation, even if you set seed and temperature 0 and all the other stuff.
Yeah, the thing I would add is that even if you take away just the GPU non-determinism, if you set the seed and you're getting sort of the exact same software behavior, but it's batching, say, 16 user requests, whether you're the first or the second or the 16th out of that batch, you're going to get different results. And I don't think any vendor wants to sacrifice their system performance to guarantee you like you're going to be a certain spot in the batch just for your own reproducibility.
Yeah, that would be my assumption, in that, like, there's a lot of shortcuts you need to take, and I believe the thinking machine sort of makes the point, like, essentially you almost never want to serve a fully unquantized model, just because, like, you're keeping track of a bunch of extra information that you don't need, end of the day. But because you're dropping that small bit of information that doesn't meaningfully affect performance, what you're doing is introducing imprecision in those floating point operations, and as such, you are defeating my GPU could be entirely clean, and as such, you could entirely, fully get a fully deterministic result from this option, like right off the bat, essentially. But I'm curious if you could, in theory, serve fully unquantized model, single GPU, maximum precision, et cetera, and end up with something that is like, yeah, the question would be, does that give you something that's fully deterministic, or something that's like much closer to a deterministic where seed would be like somewhat practical, I think?
Yeah, I mean, wasn't it that thinking machines where they actually got 100% full determinism, but it ran at like 1/3 the speed?
Did they? Yeah, I didn't actually. I got the general gist of the article, but I didn't fully read it. Did they actually perform an experiment, and they actually made it happen?
That was my understanding. Yeah, they got full determinism, but it was like at what cost? It's not worth it to go 1/3 of the speed, or have to take less users, or do less requests in parallel, or yeah. So my understanding, I haven't looked at this in like total depth either, but that was my understanding, was like they did get full determinism, but it's just much slower.
Interesting. Okay, so the forward pass is what they're leaning on, in that you can avoid atomic adds. So if you run it at full precision, then the GPU ops will allow you to do a forward pass that is deterministic. It's interesting.
One of the related things that's been going around on Twitter was, there was a paper that came out that was basically showing, if we do inference at BF16 and then we do training at FP16, we get this divergence where the inference is saying one thing and the training is saying something else. And so people were saying, okay, we need to do inference and training in the same in the same precision if we're doing the reinforcement learning stuff, because there's actually some divergence there. And there's been a lot of discussion about that, because some people are saying, well, this paper was just like some contrived scenario and it's not actually that big of a deal. But other people are saying, well, we need to kind of revisit a lot of our findings if this is true, because we kind of expected it to work out of the box. And now we're realizing maybe we were doing something entirely wrong.
Yeah, general impression I got from my ML people on Twitter was that there was like a toy problem kind of situation. Kind of same with Thinky, really, where it's like, these are interesting, but what can we do with them, kind of thing. If you're actually trying to serve the customers.
To Tom's question about small language models, my last company, that was the whole focus. It was like, okay, we can't do ChatGPT, but we can make small language models and we can customize them to different use cases. And I'm not very excited by them, because the difficulty is, like, very often right now the push is just more intelligence, more intelligence, more intelligence, and people are willing to pay premiums for smarter and smarter models. And these, like, 2 billion, 4 billion, 7 billion, whatever models, they're just quite limited. And it's difficult to, if you have one very specific thing that's high value to you and you want the inference cost low and everything, then it's good to use them. But in most cases, it's like orders of magnitude simpler to just say, go send it to ChatGPT, go send it to Claude, go do whatever, and just prompt it in the best way. And if it's a sufficiently difficult task, you can spend gobs and gobs of energy labeling data and training the model and doing all of the other tricks on top of it. And then you still end up falling short of the accuracy of a model that just gets that result out of the box, because it's so hard to get a good 2B when you're competing against a 1.6 trillion model. Like, it's just, you can't get that same intelligence out. That was just my experience, though, and especially because a lot of these providers are, like, heavily subsidizing the cost. So it's like, how much does it cost to run your 2B model locally versus just send it to ChatGPT? The GPU costs, like, if you don't have, like, complete 100% utilization, you might just be exceeding the cost that you would have sending it to ChatGPT running your own GPU. And that puts you in kind of an awkward situation where it's like you're paying for more and you're getting a stupider model.
Yeah, I think smaller models are best. They are best suited as parts, or like the place that naturally occurs to me to put them is into, if you have an LLM or a task that you want to accomplish and an LLM is involved, and you're not just straight up using a smaller model, then you can train it to do that. But if it's part of a pipeline, i.e. if there is, for instance, an LLM that's powering an agent that's doing tool calls, well, the appropriate place to put a small model there might be just for doing the tool calls, and you fine tune it on those specific types of tool calls that need to happen in this pipeline, and you put it only there. Then you let the big model that's smart call that model. And essentially the idea there is to offload irrelevant context from the main thread and have the small model be able to consistently get the tool call right, and as such be able to separate that tool calling part of your harness from something that you're relying on output from a larger, more expensive, possibly more intelligent model. And then, yeah, so if the reason to do that, and there are the companies that come to mind is like Windsurf trained SWE grep, and all it does is grep things, and they have the bigger, they saved the bigger Cascade model for doing reasoning and code editing and et cetera. And then whenever that model needs more context, it just calls SWE grep, which will go and find it the files that it needs. That kind of situation is kind of where I think small models are best suited to be at, essentially.
Yeah, I don't see the competitive advantage with them. And I think it's the deal of a lifetime right now, just to use the top proprietary models. I spend between $40 and $60 a month, and I publish 17 papers, and it has all the compute, and they get better over their lifetime. And there's always new models coming out. We should get at least 3 more, I think, by the end of this year. So I think it's all in the applications. I really do. Now, Jensen Wang said the same type of thing, like be a domain expert using this type of software. And it's not economically favorable, I think, to do anything with hardware and to just use it and then, solve the world's biggest problems, multi-prompting, different models. I really don't see any other way.
I think the SWE grep is a good example of like very often we're using a bazooka for something that actually needs a hammer. But in most people's cases, the cost and the complexity of making your own SWE grep versus the volume of the task doesn't make it worth it. So like for Cursor, the SWE grep is worth it because this is driving like all of their traffic, and that search process that they're doing is extremely valuable, and it's even higher value if they can do it fast. So in that specific case, it's very, very valuable, but at most people's companies, they're not doing something that is at that scale and justifies them going like, we need to train this model in RLHF and like all the infrastructure associated with running this model. I think that there are definitely cases, but it's relatively few. So I pulled up this link. I gave a presentation with AT&T a while ago,
There you go.
and it was kind of embarrassing because we had to submit this talk like super far in advance, and then NVIDIA had to review it, and then all of this stuff. And the whole point of the talk was basically like we took a large language model and we distilled it into a small language model, and we saved a bunch of money. But then if you look at the actual history of things, AT&T went to solve this problem at a point when it was 100x the cost per token. So GPT-4 was a certain price, and then they cut the price to 1/10 of that, and then they also released GPT-4o mini. And then at that point, it was like all of the gain that we were bragging about, we were saying, oh, we made this half the cost. But then if you just traced with whatever the state of the art was for another 6 months or 9 months, it actually got 100x cheaper. And so just the passage of time made it so much cheaper, and all of the innovations in terms of inference and just the frontier models being willing to cut their prices and stuff. So I think it's very hard to justify SLMs right now unless you have like some very high demand use case that you can justify like putting all that effort into.
It's an interesting point. I think the question of when I want a Qwen 8B versus like a GPT-5 Nano in terms of like cost, training cost, what I'm going to give people. My original thought on it was unless you are a person that's building and serving a product, and that product that you're serving involves you sending inference to the customers, then you probably don't need SLMs basically for anything except for 2 things. The 2 places you would need them is if you need to run a smaller model on the edge, such as on a mobile device, and then if you are concerned about data privacy, i.e. if you want to be able to run data or run operations on data and not have it go anywhere. Well, if you're going to send it to the big boys, then necessarily like it's theirs now. You can check the box, but at the end of the day, like the data still left. So those would be like basically the only 2 places that SLMs fit. And then they all from a I'm running a business and I'm serving to my customer side. I think that the Cursor SWE or the Windsurf SWE grep is kind of where you want it, where it's like, okay, we're getting a massive amount of these very similar requests, and we can handle the cost with GPT-5 Nano if we want, but we already have a couple of data scientists on staff. Like if we were to just run this on our own cards, like we could drop prices dramatically. on or drop costs dramatically. I think like basically those three situations are where you want SLMs. Otherwise, just use like a GPT-5 High for complex stuff and a GPT-5 Nano for like the cheap like spamming the call thing.
Yeah. Yeah. I pulled up this graph just to show the trend that I was talking about. So the graph is basically saying like, what is the cost of GPT-4 leveled intelligence over time? So over time, we get GPT-5 Nano, which is maybe even stronger than GPT-4 was, but it's actually cheaper. And so this plot is showing like, okay, this is when we started on this project, and then by the time we like went and gave this talk, GPT-4o Mini is they're saying like 240x cheaper. And so it's just interesting to like AT&T was interested in solving this problem when they have a certain use case and wow, it solves our problem. This is really cool, but it's $30,000 a day. We can't justify it. But then when you go to $3K a day or $300 a day, it's just like they wouldn't have even noticed this line item cost anymore. So they just say, do whatever with it.
There's no harm in using a bazooka as long as bazookas are pennies on the dollar. You know?
Yeah, exactly. All right. Awesome conversation, everyone. That's true. Yeah. So some of the models have gotten cheaper on paper, but in practice have stayed the same. So if you use a thinking model and then it spends 4,000 tokens to say hi back to you, then you might end up in a different cost placement. But in general, everything's gotten cheaper, even with more tokens.
Good chat, friends. Want to take off? GG.
All right. Thank you, everyone.
Thank you.
Bye, all.
Thank you.